Yo! Today we're going to do problem 1928, minimum cost to reach destination in time. This is a Leetcode hard, and by the way, that's a very accurate classification. This is a very, very tricky problem, but I think with a little bit of persistence, intelligence, intuition, capacity to learn, capability to comprehend, this is easy. EFG. Okay, so let's get right into it. So there's a country of n cities numbered from 0 to n-1, where all the cities are connected by bi-directional roads, okay? So it's a system of cities. From one city, you can get to any other city. The roads represented as 2D integer array edges, where edges I equals xi, yi time I, okay? So I'm already thinking this is gonna be a weighted graph problem, and there's one single connected component, and you can access any city in this graph where there's weighted time I edges. Okay, and it takes time, minutes to travel, okay? There may be multiple roads of differing travel times connecting the same two cities, but no road connects the city to itself. Okay, so there could be two cities with multiple edges connecting the cities. Each time you pass through a city, you must pay a passing fee. This is represented as a zero index integer array passing fees of length n, where passing fee j is the amount of dollars you must pay to pass through city j. Okay, in the beginning, you are at city 0 and you want to reach city n-1 in max time, minutes or less. The cost of your journey is the summation of passing fees for each city that you pass through at some moment of your journey. Okay, given max time, edges, and passing fees, return the minimum cost to complete the journey, or -1 if you cannot do it in less than max time. So, or within max time minutes. So I'm already thinking Dijkstra's algorithm, right? Because I'm trying to find the minimum cost to go from a source to a destination, and that cost is a passing fee. So that's a very simple problem using Dijkstra's that would be pretty quick to write out. But the additional constraint here, which makes this problem very difficult, is the fact that we have to also consider the max time constraint for approaching this problem. So you can't do things in more than max time, so you have to consider that when you look at your solution. Okay, so let's go ahead and look at this system. So we have max time 30 with edges. Let's just go ahead and see if there's something a little bit better here. So the system, let's just draw these nodes out. Trying to be fast here. All right, and then we have 10, 10, 10, 15, 10, 1, and then the cost associated, 5, 1, 2, 3, 20, 20. So when Dijkstra's runs, it's going to look at this system, and we're going to run to minimize the fee, right? So we're trying to minimize these blue values, right? Because these blue values are associated with the price that we're trying to minimize in this problem, right? So when we start at this node, node 0, and we're trying to get to this last node 5, when Dijkstra's runs, it's going to prefer this path to this one, right? Because it has a lower cost. And then it'll look at this path, and then it'll look at this path, and once it finds the destination, it'll already be done. That's because there's such a high cost associated with this system here, right? Versus in this example down here, it's the same system, but since we have the additional constraint that max time is 29, it'll consider this path and this path, but we can't actually add this additional edge because the total cost is 30, right? Because we occur 10, the total time is 30, right? We occur 10 here and 10 here and 10 here. So we can't actually take this path, right? Because although it will give us the minimum fees, it doesn't meet the constraint of the max time. So we have to run DFS, we have to run Dijkstra's in this problem, but we also need to consider the additional factor that times, we have to consider the additional factor that there's this time constraint. So what I'm going to do first is just build out Dijkstra's as we would normally do it while considering passing time, or while considering passing fares as the weight we're trying to minimize. And then we'll integrate in this idea of a time constraint. Okay, so let's go ahead and do that. Okay, so the first thing we'll do is we'll create this graph G in a cost array C, and our source and our destination in our system. So our graph is going to be blank in range passing fees. Oh, my computer's getting really hot. Damn it. Okay, our cost will be the same thing. Everything will have cost float infinity to start. Actually, this can be like that. And we just do this times length of passing fees. This can just be that. All right, and then our source is 0, and our destination is length of passing fees minus 1, right? Because we're trying to get to the end. Passing fees is the number of nodes, right? Because each node has a fee associated with it. And then we create this priority queue. So the first thing will be the value we're trying to minimize, which is the passing fee. But you start out spending a passing fee on the first node. Then the next value is going to be the actual node we're looking at, which is source. So just to make this a little clearer, we'll make that source. And then the last value we're just going to consider, or we'll just make it like this for now, since we're trying to we're not considering the max time constraint. We're just trying to build Dijkstra's out with just the system where we're trying to minimize passing fees from getting source to destination. So we'll continue doing that. We're just acting like max time is not a condition here, just to show you how Dijkstra's looks initially and how you're going to integrate in this additional parameter. All right, so while PQ, well, we're just going to call it a weight. So we have weight of U equals PQ. We're going to use the heap Q library dot heap pop from PQ. Now, if the weight of U is greater than the cost of U, so that means that we are dealing with a node that got added, but after it was added, we found something that was better. We just continue. Well, first thing we'll ask actually is if we're looking at our destination. So if U is the destination, this is the first time the destination's been reached. So that means it must have the lowest cost, because we're always popping things that have the lowest cost. So we just return W of U. Otherwise, if the weight of U is something is greater than the cost of U, then we don't have, there's no point in trying to explore this node. C of U equals W of U. And then we're going to look at each neighbor. So I need to make that, I forgot. In graph of U, we'll say heap Q dot heap push into the priority queue this neighbor, which is going to have the weight of U plus the weight of V and V. So this is a standard priority queue approach of Dijkstra's, and then if it doesn't return, if it gets here, that means return -1 because it went through everything and it never found a solution. But I forgot to make the graph. So we have 2 edges, U, V, and a weight in our edge list. So we're trying to build out this graph. We're going to say graph at U, append, and I'm trying to make it fill this form here. So append, we're going to have a tuple pair, V, and then the weight associated. And then we'll also say graph of V, append, can go to U with this weight associated. And that's really the time that it takes. Okay. So this is a standard approach of Dijkstra's algorithm, but this doesn't consider the fact that, right, if we look at this example again from our, oh, it's so slow. From our system here, right, we don't want to pick this path when the time constraint is less than 29, right? Because this path, although it has the lowest fare associated with, it can't be chosen because the time is less than 29. So what we need to add is an additional constraint, right? We need to have a conditional constraint to say, well, if we start with time 0 here, right? And then we'll say the time of U is here. Well, this weight is the time. So the weight of U is the passing fee. Sorry, I should have been a little bit more clear with my variable naming, right? Because the cost to get to the next thing is your current weight, which is the cost, plus V. WV is actually the time of V, right? This is the time it takes to get across the edge. So I'll call this T just to be a little bit clearer. All right. So this is the time of V, which we're not using yet, right? Because the cost to get to the next node, if we're trying to minimize the passing fee, is the current cost to get to me, which is WU, plus the cost, the fee of using V. Okay. But what we're going to add this additional constraint is every time we add a node, we'll also add information about T of U plus T of V, right? Because that's how much time it's taking to get to the next node. And then what we can say is, well, if T of U, right, if the time it takes is greater than, if the time it takes is greater than our max time, then we continue. So we don't consider this node, right? So we might want to check that before, right? Because if we're at destination and it's greater than time, we don't want to add that. So this would need to be flipped then. Right, so if the cost is greater than a cost we've already occurred, or the time of U is greater than max time, right? So that it's going through this system on this example here, right? It goes through this system and it gets to the destination here with the best time. I mean, with the lowest cost path, but the time is greater than our time constraint. It'll just discard and continue, right? So we can actually try this, and I think this will work for this small example because we haven't run into additional constraints yet. But also, I did do a lot of stuff here that I may not have. Okay. Destination equals destination, what? Equals destination. All right, so this works. Now, you may think, okay, we have a final solution, but the tricky part of this problem, right? Now, hopefully this is a small example that I can draw out. No, it's not, it's too big. So we're not going to draw that out. But the idea is that having the minimum cost, the minimum fare to go somewhere isn't necessarily your best solution at the end, right? Because you may get the minimum fare to go somewhere. Let me see if I can draw an example. If this is even, oh, it's still fast somehow. Okay. So let's say there's some path from the system here. You start here, so this is source. I'm drawing this cloud to represent like a system that you can go to. You draw a cloud here. And then this is your destination here. So one kind of edge case you have to consider, and the reason why this solution isn't working as it is right now, is that our solution is basically saying if the cost to getting somewhere, right, if we're at a node and we've already found a path to that node that's less, we discard it. But we may not necessarily want to do that, right? Because if we look at this example, let's say that we have t time to get to destination. So we have exactly t time, all right? And let's say that this path takes t time exactly. So this takes t time. And it costs 3. I'm just making up an arbitrary value, okay? So let's say it costs t time, takes t time to get here, and our fare is only $3, okay? Now let's say, and then this additional thing costs 1. So we can't get to destination. If we take this path, we can't get to destination because it's going to take t plus 1 time, right? Now, if we have this system over here, let's say that this blue system, or let's color it yellow. Let's say this yellow system takes t minus 2 time, but it costs 7. Right, so when Dijkstra's runs, it's going to prefer this path first, and it's going to say, okay, this node costs 3. And then it won't be able to continue because it's used all of its time up, so it won't be able to get to destination. So then when this system runs, it's going to end up getting to this node again, and it's going to not be able to continue because it has cost 7, and since it has cost 7 and this node has found a cost 3, it's going to say, well, it already found a path here with cost 3, so I can't continue. But the issue is that this cost of 3 path is not valid, right? Not valid. This cost of 3 path is not valid, so it shouldn't have rights to this node, right? Because the cost 7 path actually can get to the destination. This cost 3 path can't. So just because a node has a cost that's smaller than your current cost doesn't necessarily mean that that's the path that you're going to take, because that lower cost path may not be able to reach the destination. Now, the only way that this cost 3 path can be better is if it has a lower time, right? If something reaches this node with less time than another path, then it can only be better, right? Because it can get there with lower cost, which is great, and it can get there with less time. So if it can get there with less time, then it's going to be a better path, right? Because we're just trying to get to the destination. So if this thing has less time than I do and it costs less, then it's certainly a better solution. Okay, so what that means is then our cost is no longer the cost of you, right? Because the cost of you is the cost of me in terms of fare, right? So what it really should be is if the time of you greater than the cost of you. And that would mean then that the cost of you equals the time of you instead. Memory limit exceeded. Interesting. It's weird. Alright, so I'm doing something wrong here. Oh, because this is getting changed here. I don't want to change it. Forgot to change it back. Oh, what am I forgetting? I'm trying to see if I'm... What am I doing wrong here? Okay, well that's not good. Oh, less than or equal. Duh. If the cost of U is less, then U has already been but I don't need to check that here now. Oh, this is so confusing. If the cost of U is less, then it's not float infinity for sure. And that means that it's already been traversed. So it means since it's already been traversed, that means it has a lower cost. And if it has a lower time, that means that it was already been traversed with less time, so we don't need to do it again. So that seems right. But my runtime isn't good. Why? Why is not my runtime good? What am I forgetting? I swear this is what I did before. Alright guys, I'm gonna look at another solution I did. I just can't believe I'm forgetting something I literally just did. I don't know what I did differently. It's so weird. Oh, greater than or equal to. Yep, that's right. Ugh. This shouldn't affect my runtime so much. Because if it's the same amount of time, then it's still better to use the previous solution the same amount of time because the previous solution had lower cost. Man. That's so crazy that one little thing. Okay, so that's it for this problem. What's the runtime? Well, what's the runtime of Dijkstra's again? So we can add each edge. So I'm not exactly sure what the runtime is on this. It's a little complicated. So Dijkstra's is E log E, right? So each edge could be added. But we have time edges, and so I'm going to say it's max time times the number of edges. So it's definitely big O of this. Now, there's probably a tighter constraint, but it's definitely big O of that. Now, exactly what the runtime is, that's up for debate. Like, this is a very complicated problem because there's this idea of time, but it's definitely big O of that. All right, with that, I'm going to call it.